Good morning everyone. So recall that in the last class we introduced the concept of kernel and range and then the rank and nullity. Today we are going to discuss one and onto linear transformation, which would lead us to the concept of isomorphic vector spaces and isomorphism between linear transformation. So we begin with the definition. Let T v to w is a linear transformation, then we say that T is 1 to 1 if T maps distinct vectors in V into distinct vectors in W, which means that if T of U is equal to T of V, then U should be equal to V, which also means that if U is not equal to V, then T of U should not be equal to T of V. And onto every vector in W, which means that for every W in W, there must exist a vector V in capital V such that T of V is equal to W. So check if the following transformation is 1 1 and onto. We will start with 1 1. So let us assume that T of A is equal to T of B. That gives me A transpose is equal to B transpose. If I take transpose on both the sides, then A transpose of transpose is equal to B transpose of transpose. That gives me A is equal to B, implies T is 1 to 1. For onto, I must start, let's say this is my W, this is my V. So I must start with let A belongs to M22. Then if A is any matrix, its transpose always exists. So then there exists A transpose belongs to M22, where M22 is V, such that T of A transpose is equal to A, because I know that T of A transpose means A transpose of transpose. It means that whatever vector you take in W, which is M22, there always exists a vector. We have shown that we need to find this vector. So there exists a vector in V, which is M22, such that T of this is V and this is W. So T of V is equal to W, T of A transpose is equal to A. And hence it is 1 1 and onto. Again, by definition, if we check, then T of x1 y1 is equal to T of x2 y2. That gives me 2x1 x1 minus y1, 0 is 2x2 x2 minus y2, and 0. If you compare, then you get x1 is equal to x2 and x1 minus y1 is equal to x2 minus y2, implies y1 is equal to y2 since x1 is equal to x2, and that gives me x1 y1 is equal to x2 y2, implies 1 to 1. Now if I have to check onto, then I have to see that for every vector in R cube, so let me take any vector 0 1 2, which is in R cube. Now since here it is 2 and I know that the transformation xy takes us to a vector in R cube where the last entry is 0. So for this vector 0 1 2, there does not exist xy in R2 such that T of xy is 0 1 2, implies not onto. Yes, so I got a counter example where I found a vector in R cube such that there does not exist a vector in R2 whose image is the required vector. What about this one? Is it 1 1? Is it onto? if I start with 1 1 and if I take two vectors, let's say x plus 1 and x plus 2, so they are unequal. So the result says that if u is not equal to v, then t of u should not be equal to t of v. But if I apply t on both the sides, then it is the differentiation. That gives me, if this is p and this is q, then p dash is equal to 1 and q dash is equal to 1. So you can see that u is not equal to v or p is not equal to q, but p dash is equal to q dash, hence it is not 1 1. Now for 1 2, again you take any vector in p2. So let ax square plus bx plus c is in p2. Then we claim that there exists integration of ax square plus bx plus c, which is v, in p3, such that t of v is ax square plus bx plus c, because t of v means you differentiate this vector which gives you ax square plus bx plus c, and this is why it is 1 2. Now we can observe here that it is not very easy to check 1 1 and 1 2 through definition, and therefore we will move to some interesting results. So the first result says that t is 1 1 if and only if kernel t is 0 vector. So very interesting result. It means if you find kernel t, if it is not 0 vector, it is not 1 1, otherwise it is 1 1. The proof is also very interesting. Let's see kernel t is equal to 0 vector, and I have to show t is 1 1. So I start with t of u is equal to t of v. That becomes t of u minus t of v is 0 vector. That becomes t of u minus v is equal to 0 vector. That means that u minus v belongs to kernel t, but kernel t is only 0 vector. That gives you u minus v is equal to 0 vector, and that gives you u is equal to v, implies 1 1. Yes, now let's assume it is 1 1. I have to show that kernel t is 0. So let u belongs to kernel t. I have to show u is 0. U belongs to kernel t, then t of u is 0. Also, we did a theorem which says that t of 0 is always 0. From these two equations, if you compare the left hand side and right hand side, you will get t of u is equal to t of 0. But t is 1 1. That gives you u is equal to 0. And that means that kernel t is the 0 vector. Okay, so please do remember this result. We are going to use it many times. The next result says that t is onto if and only if dimension of range t is equal to dimension of w. So this directly follows from the definition. Even we will do this result that when dimension of rt is equal to dimension of w, it means that range t is isomorphic to w. And since they are isomorphic, it means they are almost equal. In some sense, we can feel like this. And therefore, when they are equal, then it means when r of t is equal to w, then you can always see that whenever you take an element of w, there exists an element v in capital V such that t of v is equal to w. So now you can recall one of the example which we did, and here you can see that dimension of R3 is equal to 3, but dimension of R2 is equal to 2, and that's why we found a vector for which there does not exist xy, so that xy is the required vector. If dimensions would have been equal, then it would have been on. Let's see some exercises. Before that, one more interesting theorem says that if the dimension of V and W are equal, which is n, and T is a linear transformation from V to W, then if it is 1 1 it must be onto, and if it is not 1 1 it is not onto. It means it is sufficient to show either 1 1 or onto. It directly follows from rank nullity theorem, which says that rank T plus nullity T is equal to n. Now if kernel T is 0, it means nullity is equal to n. So it means rank is equal to n. And rank is equal to n means dimension of RT is equal to dimension W implies onto. If you start with onto, which means rank is equal to n, that gives you nullity is equal to 0, which means kernel T is equal to 0. It also gives us a very important information that if dimensions are not equal of V and W, then both the T cannot be both 1 1 and onto. One of them is possible but not. Again directly follows from rank nullity theorem. So this is an example. Check if it is 1 1 and onto. So I used the previous theorem which says that kernel T is all those A, B, C, D for which T of A, B, C, D is equal to 0, which means is the 0 matrix of M23. Now if I solve it, then I will get the following equation: A minus B is equal to 0, C minus D is equal to 0, A plus B is equal to 0, C plus D is equal to 0, and all these equations gives me A, B, C, D is equal to 0, which means that the kernel T is the 0 matrix and therefore 1 1. Yes, now I have to check onto. Now I directly use the rank nullity theorem to check onto. So now T is 1 1, that means that rank T is equal to rank plus nullity is the dimension of M22. So which is 4, 4 minus 0 which is 4. But dimension of M23 which is W is 6. 4 is not equal to 6 implies not onto. So if it is 1 1 it cannot be onto because the dimension of V and W are not equal. This is what I told in the previous slide. So I have added a complete solution here. Think over it that what do you say about this one? Is it 1 1 and onto? Yes, if I follow the definition, if I try to find the kernel T, it is not very easy. But what interesting is to observe is that T of identity matrix is A times identity matrix minus identity matrix A, and that gives me the 0 matrix. This means that the identity matrix belongs to kernel T. It means that kernel T is not the 0 vector. It has at least one non-zero vector. It means T is not 1 1. And dimension of V and W are same. So therefore T is not onto. So very interesting approach which you can see here. What do you say about this one? Is it 1 1? Is it onto? By definition it's clear that it cannot be onto, and if you find the kernel T, then you will get y is equal to 0, z is equal to 0, but x is not equal to 0. So your kernel T is x 0 0, where x belongs to R, so not 1 1, and there are two variables only, so therefore dimension of range T is equal to 2, which is not equal to dimension of R4, implies not onto. So this is an example which is neither 1 1 nor onto. This one is straightforward. Please try by yourself. You will observe that it is both on 1 and on 2. So if a linear transformation is both on 1 and on 2, we say that T is an isomorphism, and under this condition both the vector spaces are isomorphic. So if T is both 1 1 and 1 2, then V and W are isomorphic. But if T is not 1 1 and 2, we cannot claim that V and W are not isomorphic, because for V and W there may exist some other linear transformation which is 1 1 and 1 2. So every n-dimensional vector space is isomorphic to Rn, which means that Rn and Pn minus 1 both have dimension n are isomorphic. And it's better to say that if I have to check V and W are isomorphic, it means I have to check their dimensions are equal. So V and W are isomorphic if and only if dimension V is equal to dimension W. So if I quickly see this one, I have to check that whether V and W are isomorphic, which means I simply have to check that does their dimension equal. So dimension of W is equal to 2 is already given. For V, it is defined as A11 minus A11 because trace A is 0, where Aij belongs to R. This means there are 3 variables, dimension of V is equal to 3. Dimension V is not equal to dimension W, therefore they are not isomorphic. Here both the dimensions are same, implies isomorphic. If you see the next one, then dimensions are not equal, it's n plus 1, it is n, so V is not isomorphic to W. If you see this one, then dimensions would come out to be equal. Here the dimension is 3 and dimension of W is also 3. Please do try by yourself, it's very easy, and therefore they are isomorphic. The last one, the diagonal entries, which means V looks like A11, A22, A33, and all other entries are 0. Therefore dimension V is equal to 3 is dimension W, implies V is isomorphic to W. Here also V is isomorphic to W. Okay, so that's all from today's class. The last topic of this module is to find the inverse and compositions of the linear transformation. Thank you very much.